So in our introduction, we're learning that so the first kind of system that I want to talk about is called a closed system or a control mass. And it's any fixed quantity of matter. It could be the air inside a balloon or the liquid inside a syringe. It could be the air and the people inside a car. It could be the water inside a cup. It's any fixed identity amount of mass. A really quintessential example of this is a piston cylinder. It's a really common example, cylinder. It's a really common example in mechanical engineering applications because of the internal combustion engine. Schematically, we show it as piston being just this rectangle and the cylinder being the cup around it, cylinder. But importantly, we don't care about either the piston or the cylinder. They create the system, which is the quantity of matter inside the piston and the cylinder. Could be a quantity of liquid, could be a quantity of gas, could be a mixture of the two, could be a solid for all we know. It's the stuff inside that boundary. So we usually draw the system boundary as a dotted line. And in this case, the system boundary is real and physical, meaning that it coincides with the walls of the cylinder and with the head of the piston, but it doesn't include any of the steel or glass or plastic that make up that cylinder and that piston. So the system is what's inside, and the surroundings would include the piston and the cylinder material and the air or the environment outside. But if we think of this system, then this system has a few things that can happen with it. The piston can move up and down as long as it's not pinned or restrained in some way. And so this upper boundary can move. And in moving, it can cause work or do work and cause work to flow in or out of the system. You could compress what's inside, or what's inside could expand out and push on the environment. But we could also add energy or heat in or out of the system to change the energy of that system. We could heat up the gas inside a piston or a balloon and cause it to expand. We could likewise cool it off and cause it to contract. So closed means that the boundary is closed, and control mass means the mass is fixed. Doesn't say anything about whether or not the boundary can move, doesn't say anything about whether or not energy can be exchanged by work, therefore, or whether the boundary is insulated, or whether the boundary can permit energy exchange by heat transfer. What it does, however, indicate is that there is no mass transfer here. The mass is fixed, so there is no mass transfer across this boundary. In comparison to a closed system, an open system or a control volume is obviously different. And it is different in that we can have flow in or out of the device, which means we can have flow in and out of the system that we are using to model this device. And a quintessential example of this would be a turbine, or a mixing chamber, or a heat exchanger, anything where you've got flow. So a typical schematic is this box with one inlet and one outlet. And the system is, again, not the box. It's the stuff that the box contains. So again, we'll draw a dotted line for our system boundary, and we can have portions which are a real boundary, and we can have portions which are an imaginary boundary, And through those imaginary boundaries, which are really just, areas that we're considering, we might have an area which is the inlet, which permits mass to flow in, or areas that are outlets, which permit, obviously, mass to flow out. With those mass inflows and outflows, the system is whatever mass right now is within the box. So if it's filled with air initially and then you flow in water, well, you've changed the mass inside this control volume. But the control volume is literally the space inside this box. We can have real boundaries, we can have imaginary boundaries, but we can also have work in and out, just like before. We can also have heat flow in and out, just as before. And so this is the biggest difference between a closed system and an open system. They both have work and heat in and out. They can both have moving boundaries, fixed boundaries. They can both have real boundaries. Control volume is typically going to have some imaginary parts of the boundary, which are the inlets and outlets, and are going to have mass flow rate, whereas a closed system doesn't. A control volume is not a fixed chunk of mass. It's whatever mass is inside the volume under consideration. So we've talked about control masses and control volumes. There are some special cases which can apply to control masses or volumes. And we give them certain names. One of those names is adiabatic. This means that it is there is no energy flow by heat. This could be because the system is really well insulated. It could also be because the process happens so quickly that there's not enough time for heat transfer to occur appreciably. Obviously, this is a simplifying assumption. There's no such thing as perfect insulation. There's no such thing as so fast that heat doesn't transfer at all. It's an assumption of it's a small amount, so let's approximate it as a zero amount. It's also a what-if tool. You can ask the question, what would happen to this system if there was no heat transfer, if it was adiabatic? And then say, well, okay, knowing that, what is the effect of a small amount or a large amount of heat transfer on top of that behavior? Another special case is rigid. This applies to control masses only. And it's where the boundary doesn't move. So therefore, there can be no work input or output. So it's the difference between a syringe or a piston cylinder where you can move the plunger, or one where you can't, where you've put a pin in the plunger and it just cannot move. If it's pinned, it's rigid and it can't move. Otherwise, it's not. It's also the difference between, say, a balloon. If you put a balloon inside a hole that is balloon-shaped, well, it's deflated, you start blowing it up, it can expand, eventually it hits the extents of that hole and now becomes rigid, it can't expand anymore. Finally, the last one is isolated, which is just a rigid and adiabatic system, which means no work. No work and no heat transfer. Which might seem like a weird thing to think about, but you can still apply thermodynamics in this case. You can remember that a system can be a system of systems. So you could have a really well insulated rigid box, but inside of it you could have a partition, and on one side you could have compressed air, and on the other side you could have a vacuum, or you could have liquid, or you could have less compressed air. And then you could imagine or model what happens when that boundary is removed. Well, it's well insulated so that nothing happens with the environment in terms of heat transfer, and it's rigid so nothing happens with the environment in terms of work transfer. But you can still consider what happens to the system inside, which used to be compressed air on one side and whatever on the other, and is now the two things interacting. Thermodynamics makes a lot more sense when you start applying it to things. So let's think about some examples of where we would apply these ideas of open and closed systems to model certain things. So for example, let's think of a soft drink or the canned beverage of your choice that you've taken and placed into a fridge to cool off. Open system or closed system? Well, think about it for a second. The mass is fixed. The mass in this case might be the beverage inside the can, it might be the beverage and the can, but regardless, the mass is fixed. Nothing's going to change of that mass over time. So therefore, it's a closed system, and it's in control mass. It's not adiabatic, especially if you're trying to model the cooling of it in a fridge or the heating of it on a counter. It's not it's not fully rigid, because obviously you can squeeze a can and it can change a bit, but it's pretty rigid. So you would probably model it as a rigid, non-adiabatic closed system, unless you were caring about the stretching of the can as it heats or cools, and the stresses that generates on the wall of the can. Another example. High pressure steam going through a turbine, powering a generator. So basically the quintessential way that we all get electricity. Almost every process eventually, or most processes, eventually come down to you've heated up some water to steam and you put it through a turbine. Well, in this case, we have mass, the steam, flowing through a device. And you have, through the boundary of the device, and therefore it's an open system. And again, we care about the steam in this case, not about the turbine itself, but we care about the steam in it, flowing through it, and it is an open system. Steam can flow in, steam can flow out, so we would model this as a control volume. As a third example, let's consider a lake and a power plant. Many power plants use a nearby body of water to help cool them. They pull in lake water, they use it to cool off their systems, and then they dump that water back into the lake. Has environmental impacts. If you design it well, doesn't have too many. If you design it poorly, yeah, you certainly impact the environment in the lake by dumping in that hot water or that warm water. But let's consider this system thermodynamically. Where do we draw the boundary for this, and is it an open or closed system? Well, that's an interesting question. If you draw the boundary around the lake, it's a control volume. So if your boundary is around the lake or the plant, then it's a control volume. It's an open system. Water can flow in and out of the lake. Water can flow in and out of the power plant. So it's an open system. And therefore, we model it with a control volume. However, if a system can be a system of systems, so there's nothing stopping us, in a thermodynamic sense, from considering a boundary around both the lake and the power plant. And so if our boundary goes around, if we place it around both the lake and the plant, well, then we have the mass fixed. And we have a closed system. And therefore a control mass. I'm going to frequently simplify control to C, or control mass to Cm and control volume to Cv. You'll also probably see me write TD as thermodynamics. But going back to this example, both of these system boundaries work. Both can work, at least. Some are more complex than others for given situations. The choice of how to do this is, well, is up to the engineer and is based upon experience. One obvious thing that might be occurring to you right now is, well, wait a second, lakes have water flow into them and out of them, so independent of whether they're used to cool a power plant. And you're right. If you're drawing your boundary around the lake and the power plant this way, what you're assuming is that the lake has some constant properties based upon that inflow and outflow of the rivers that come in and out. But again, if you're wanting to consider the larger environmental impact of this power plant, you are going to need to consider that and how it therefore affects the outflow from the lake versus the inflow, or how it affects the lake itself. So I can't emphasize it strongly enough that the system, the thermodynamic system, is enclosed by the boundary, and that's always the case. And that where you place the boundary is almost always going to exclude the actual container. And so the system enclosed by the boundary is almost always the matter, the mass, the stuff, the material that is inside the device or the container, and is typically, in mechanical engineering, water, air, or if you're dealing with cooling systems, refrigerant. Again, you can apply thermodynamics to anything. You can apply it to lead, you can apply it to plastic, you can apply it to any matter, silicon, etc., etc. Typically, mechanical engineers are going to be working with working fluids of water and air or refrigerant. And typically, when you're dealing with control masses and control volumes and thermodynamics, you're taking the device as a black box and considering what it does to the matter inside of it, to the system inside of it, to the working fluid inside of it. So this is where we bring in the idea of material properties. So a system is a hunk of stuff, and the condition of that system is called its energy state, or its state, and is described by its properties. You know some properties already. For example, there's temperature, T. Another really common one in thermodynamics is pressure, P. We will also very often deal with volume, which I will strive to put a little bottom hat on. Think of that as a cup with a liquid level in the bottom of it. We give it that symbol to keep it distinct from V velocity that you'll use in fluid mechanics next term. We also obviously deal with mass, denoted M, density, denoted rho, viscosity, how thick how thick a liquid is a property. Surface tension, how much it pulls itself into a spherical shape, is a property. Electromagnetic permittivity is a property. All of these material properties, based upon the molecular state of it, are thermodynamic properties. The big ones that we're going to use in this course are up here, are these top 5. There are others. Don't forget that there are others. Temperature, it's related to the internal energy, to the internal kinetic energy of the molecules itself. Pressure is related also to the internal energy, but very specifically to the momentum of those particles as they move. So neither one of them is a direct measure of internal energy. Internal energy is itself a property that we will bring in a couple of lectures. Volume, it's related to the amount of matter, mass as well. And density is obviously a combination of mass and volume put together. Properties also include kinetic energy and potential energy. So all of these are properties of a system. But let's look at these properties and start categorizing them to make some headway. So one of the categorizations that we need to consider when we're thinking about properties is what's called intensive versus extensive properties. So an intensive property is one that is independent of the mass of the system, and to denote these, we usually use lowercase symbols. So this is things like lowercase p, or mu for viscosity, or sigma for surface tension, etc., etc. And an extensive property, on the other hand, is a property that does depend on the size, or the mass of a system. And we usually use uppercase symbols for this, or uppercase symbols for this, uppercase letters, etc. for this. Well, so which are which? Here's a system. It's got some mass, temperature, pressure, volume, and density here. Well, which are which? There's a really simple trick. And that simple trick is to divide the system into 2 halves. So it's the exact same thing. We've just thumped it in half. And then ask yourself, what is the property in that half system? Well, if we take an apple and cut it in half, we have two halves, one of which has half the mass of the apple, and the other of which has half the mass of the apple. Likewise, volume, let's actually put that little hat underneath there to remind ourselves. Likewise, it has 1/2 of the volume of the apple in one half, and 1/2 of the volume of the apple in the other half. However, the temperature of 1/2 of the apple versus the other half of the apple hasn't changed. The pressure of 1/2 of the apple versus the other half hasn't changed, although it's a little bit weird to think about the pressure of an apple. The density also has not changed. So I realize that I just used a capital P here. You're going to find that people really commonly write a capital P for pressure. It's one of the exceptions to the rule of typically you use lowercase for intensive properties. One that you'll always see is that temperature is capital T, or almost always. Some people call it theta. And that's to distinguish it from lowercase t, which is time. This is one of those instances, and there's many, where language, spoken language, and certainly colloquial spoken language don't match up with scientific parlance. So it would be lovely if we could have perfect clarity in all of these things and follow our sign conventions, but we also need to consider how humans talk, and they talk about temperature and time and need a way to distinguish them. So you're smart, you can handle that. So the reason we care about intensive versus extensive properties is that, well, the intensive properties are rather nice to work with because we don't need to worry about the mass of the system. But at the same time, we need to care about the extensive ones because, well, the total amount of energy often is going to depend upon how much you have of something. If I have 1 liter of compressed air, that is a lot less energy than 1 cubic meter of compressed air at the same temperature and pressure. And so we're going to need to care about the difference between them. And we're also going to need to convert between one and another because it's really nice to work in intensive units when we can. But something which comes to our aid is the fact that you can make an extensive property into an intensive one. And in fact, it's quite easy. So for example, let's consider volume. Where did my pen go? Let's consider volume, which is obviously extensive. And now let's define a little lowercase v, it's that little curvy v there, which is volume divided by mass. Well, this is now what we call specific volume. And it is an intensive property. If you pause and think about this for a second, you might notice that it's also 1 over density. Density is mass by volume, so volume by mass is 1 over density. This is one of those weird bits of thermodynamics. I would love it if thermodynamics worked in density rather than specific volume, but you don't in thermodynamics. In thermodynamics, you think in specific volumes. So just heads up, get used to it. We'll do this. We'll see this done very, very frequently. There's a lot of extensive properties to come, like internal energy, like enthalpy and entropy and exergy, some of which we get to in this course and some of which come in 354. All of those depend on the amount. And the easiest way to think of that is internal energy. How much energy is in 1 liter versus 1 cubic meter of compressed air? Well, obviously it depends upon the amount of compressed air. So energy, hopefully you can feel, is an extensive property, but we will very frequently work with the intensive property of energy just because it is easier to work with. So all of these properties that we've been talking about are what are called state variables. They're variables that define the state of a system. And for them to exist and be well defined, you need to be in what's called an equilibrium state. So an equilibrium state is a state of balance in a system. And if you think of the system being, say, the water in a cup, for there to be a single defined density, you need a state of balance in that system, which means all of the water in that cup needs to be at the same temperature and the same pressure, neglecting hydrostatics. And if that's the case, then all of the other properties, its density, its viscosity, etc., are going to be defined everywhere and equal everywhere. So an equilibrium state is one for an internal system, or inside a system, it's one where there's no temperature distribution, there's no pressure distribution except hydrostatic, there's no chemical reactions going on, there's no phase change going on. It's, if you walk away from it and come back, it's not going to look different, assuming nothing's happened to it from the external. You can also talk about external system plus surroundings equilibrium, and for those to be in equilibrium, there needs to be no heat transfer between the two. There needs to be no work transfer. There needs to be no mass transfer. Again, if you walk away and come back, nothing should change. So you can have partial equilibrium or full equilibrium. You can have equilibrium maintained by, say, a well-insulated boundary. And then if you remove it, well, it's no longer in equilibrium because now the temperature change can drive a heat flow. But regardless, the little nugget in here is that to define a state variable, a property, to be well defined across an entire system, that system has to be in an equilibrium state so that every point is at the same temperature and pressure and density and etc., etc. And this relates to what's called the state postulate. And so the state postulate is the fact that for the types of systems we're going to consider in 250 and in 354, once you specify two independent intensive properties, everything else is fully defined. So let me break this down. Independent means that you can vary one. Can vary one without changing the other. So for example, the air in the room, you can change the pressure, you can put it into a syringe and squeeze it, you can change the temperature, you can take that syringe and put it into hot water, and you can change the two independently. You can't, for example, vary specific mass and density independently. As you change one, the other one has to change because one is the inverse of the other. To further break this down, simple compressible system is written there, and I didn't say what that was. Simple compressible systems are the ones you're going to deal with in 250 and 354. Simple means single material, and compressible means can exchange work by moving the boundary. So you can compress a syringe or a balloon or a piston cylinder. It is compressible. It means that you can't exchange energy by kinetic or potential. If you need to model that, then you need more independent extensive properties. The independent extensive property for gravitational potential energy is height. The independent extensive property for kinetic energy is velocity. So if you need to bring those in, you bring them in. But if you're just considering something where there's internal modes of energy transfer and compressibility effects, then it's a simple compressible system, and you only need two independent intensive properties. So for an example of that, what is the equilibrium state of water when it is at 25 degrees Celsius and a pressure of 101.3 kilopascals? So I picked a really specific point there, that is standard temperature and pressure, or at least it's one definition of standard temperature and pressure. And so the state of water at that temperature and pressure is fully defined. You know that it is liquid phase. You know it has a density of 998 kilograms per meter cubed. It therefore has a specific volume of 1 over 998 meters cubed per kilogram. Oh, let's see, it has a surface tension of about 0.0723 newtons per meter. You don't need to know that. It's just drilled into my head. I will never forget it from my master's and PhD. It has a viscosity of, it has a vapor pressure of, etc., etc. From your Chem 102 class, I hope you remember that you can look up all of these properties, and specifically, you don't need to know all of them. As soon as you know two, temperature and pressure are usually the easiest two to know, you know all of the rest. But it works both ways. If I told you you have some water, you've measured it the density to be 998, and you know the pressure is 101.3 kilopascals, you could tell me what the temperature of that water was, because all of these are interrelated. So the state postulate is that properties are interrelated, and for a simple compressible system, as soon as you've specified two, as soon as you know two, all of the rest are known or can be looked up, are fixed. So we've talked about the properties of a system and how the system has to be internally in equilibrium for the property to be constant, uniform, defined across the entire system. And we call those state variables because they define the state of the system through the state postulate. The last thing to talk about for systems, at least at this introductory level, is processes and process variables and paths of processes. So a process is to do with the fact that a system will change, right? Thermodynamics is energy forms and their conversion. So a system can undergo a change, a conversion, from one equilibrium state to another, by following some process or some path. And that process or path is the series of states that the system passes through. So these states that the system passes through are usually considered to be quasi-equilibrium states. That means that at each state, the system is in equilibrium instantly at every instant in time. So let's look at this with an example. Let's consider a piston that we are moving from some V1 to some V2. So, and let's plot pressure versus volume. So we've got some V1, which is larger, and some V2, which is smaller. Hopefully, your intuition tells you that the curve would look something like this, therefore, where you go from some lower pressure, P1, to some higher pressure, P2. That curve is the process path. And that curve is describing the pressure inside that piston cylinder as you push from one volume down to another volume. In thermodynamics, to make progress, to model things, we will often have to consider slow compression. That means that at every point along here, you are at quasi-equilibrium. And the reason for that is back to that idea of a state variable. If you push quickly and cram all of the pushing up near the piston head, you can do that, but now you don't have a single defined pressure inside that system. So you can't say that there's a single pressure versus volume if you're pushing too quickly. Slow is not that slow because pressure equilibrates at the speed of sound. But you can certainly push fast enough to not be in quasi-equilibrium. So just as a reminder and to write it down, quasi-equilibrium means it is at equilibrium at each instant in time. And again, that's so that you can define a single pressure or a single density or a single temperature across the entire thing. So that's a process and that's a path. A path variable is work, is the work that it takes to do that compression. Because if you think about it, to begin with, the pressure is low. It takes some force to push that piston in. As you do it, the pressure goes up, and so it takes more force, more force, more force. So there's going to be, dependent upon the path that you take, an amount of work that it took, and that work is what's called a path variable or a process variable. And that ties into the fact that the shape of the curve, and therefore the amount of work that it takes to compress that cylinder, depends upon the process path that you take. And therefore, or to say it a different way, it depends on the process. So the shape of the curve, and therefore the work necessary, depends on the process path that you take. And as usual, to make progress, we consider some idealized models. We think about some simple cases that we can approximate things as, so that we can do some what-if analysis. What if we did it this way versus that when you're considering designing something? So there are some idealized models that you'll frequently use in thermodynamics. One of them is what's called an isothermal process. Iso means the same. So isothermal means constant temperature. That means as you are compressing that gas in that syringe, the temperature doesn't change. Now, if you've ever experienced compression or expansion of gas, you know that the temperature does change. So to have that isothermal process, you would have to pull out the heat as you're compressing it. So maybe you'd go nice and slow and put it into a big water bath so that you're pulling the heat out. You could also have an isobaric process. Bar as in bars of pressure, being a pressure measurement. So isobaric means constant pressure. And so that's most definitely not the curve that we had on the previous slide, because if it's constant pressure versus volume, well, that's a straight line like that. And that's not the curve that we had on the previous one. To do that, you need to pull out the heat and then some, so that as you're, if you think of PV equals nRT, you need to pull out more and more and more heat and drop the temperature lower and lower to keep the pressure down as you're decreasing the volume of that fixed amount of air. You can also have an adiabatic process, which means no heat transfer. No heat transfer Q. So this could be a well-insulated syringe, or it could be one that you are compressing so quickly that there's not an appreciable amount of time for the heat to flow in or out of that syringe. And then the last one is what's called a polytropic process, which is just the name given to one where it's well modeled by pressure is equal to volume to the n times some coefficient c. They're both constants, c and n. It's a way to generally capture all of the above. If you throw in different values of n, you can get those above processes. You can get other processes as well. We'll come back to this. We'll come back to processes, isothermal processes, isobaric processes, etc., etc. But just picture in your mind for a moment that certainly the pressure versus volume that you'd have in that syringe would change depending upon how you compressed it and what else you did to it. If you were adding heat to it or removing heat from it or preventing heat from flowing. And also think about the fact that as a result, it might be really easy to compress that syringe or really hard to compress that syringe. So the amount of work depends upon the process, which is why work is called a process variable. So we'll leave it there for now, and come on back and do some more about energy and conservation of energy in the next lecture.